Hello world and hello maths fans. Thank you, voice. That went well. Sorry, that was just super groggy. All right. Hello world, and hello maths. Hello world and hello maths fans. Today we will be talking about logic. Logic allows us to draw conclusions from given information. It's also the basis of most of computer science. In today's chapter, we will begin by looking at a puzzle involving werewolves, where we will see how to follow through an assumption to its logical conclusion. We'll then move on to the definition of a logic gate and look how these foundational building blocks can be used to construct more complex systems. This will include the universal logic gates NAND and NOR, which can be used to build all others. We'll then end with an ultimate logical puzzle in the form of a problem called an Einstein puzzle, which is a type of puzzle. I've said puzzle like 12 times. Sorry. All right. We'll go again. Why are intros always the hardest? Tell ya. Okay. Come on. Okay. We're talking about logic. Logic allows us to draw conclusions from given information, and it's the basis of computers. Hello world and hello maths fans. Today we will be learning about logic. Logic allows us to draw the correct conclusion from given pieces of information, and it is also the foundation of computer science itself. We begin our discussion with a puzzle involving werewolves, where we will see how to follow through an assumption to its logical conclusion. We will then look at the foundational building blocks of logic, known as logic gates, which can be combined to build complex circuits. This will include a definition and discussion of NAND and NOR, the universal logic gates that can be used to build all others. We will then conclude by solving the ultimate mystery in the form of an Einstein puzzle, a type of problem favored by one of the greatest minds of the 20th century. Logic gates are the tools by which a computer understands logical statements. They are defined as follows. We say a logic gate is a device that takes inputs from a two-element set. We refer to such a set as Boolean, and produces an output from the same two-element set, from the same Boolean set. Now these elements, these values, are often written as 0 or 1, false or true, or off and on. So 0 here being false and off, and 1 here representing true or on. Now, given this definition, we can now begin to talk about types of logic gate. So no, we're not, because I forgot what slide it was. Should I start again or go from end of slide?
Let's just start again.
OK. Logic gates are the tools used by a computer to understand logical statements. Let's look at how we define them. So the formal definition says a logic gate is a device that takes inputs from a two-element or Boolean set and produces an output from the same two-element set. Now these elements are often referred to as any of the following. Sometimes they'll be written as 0 and 1. Sometimes they can be called false and true, and other times off and on. So 0 here would represent false, and off and 1 is the same as true or on. Now the gate itself can take in a single input. So we can have an input from our two-element Boolean set through the logic gate and provide an output. We could also have multiple inputs. So here, for example, we could have two different inputs, A and B, passing through our logic gate and giving us an output. And again, there can be more, but today we will just focus on 1 and 2 input gates. Now, one of the first logic gates that we might be interested in, or that we might come across, is something called the AND gate. So the AND gate is used when we want both inputs to be true, to be on, both of them to have that value of 1. And in that situation, when both of them are 1, then that is the only situation where the AND gate will produce 1 as the output. Any other combination of inputs will actually give an output of 0. We must have both things to be true. Now, an example here where you might see this practically is if I was doing some online shopping and I wanted to search through the products and I wanted to find a product that was both under $10 and had a minimum of a 4-star review. Now, in terms of what actually happens with these inputs passing through the gate, just to really spell this out for us, if we have two 1s going in, so both of our conditions are true, then the AND gate will produce the output of 1. We have required A and B to be on, to be true, and so therefore the AND gate produces that positive output with 1. If we have a 0 and a 1 going into our gate, now one of them is on, but the other one is not. So the AND gate is going to produce that 0. Similarly, if the order is switched, we're going to get the exact same output. Only one of them is on, only one of them is true, so we would get a 0 again. And finally, if both of them are false, if they're both off, then we're going to get the output of 0. So we've now covered all possible combinations that could go into our logic gate, our AND gate, and we can summarize them in what is known as a truth table. So we read a truth table where the first column shows the input of our first variable, A. The second column is showing the input of B. So just like we saw in those diagrams, and then the third column is giving us our output according to the specific logic gate that we are looking at. So here, A and B is given in that third column, and this is just summarizing what we've just seen on the previous slides with those diagrams. Now, from an AND gate, we then move on to the OR gate. So the OR gate is when we require at least one input to be true. So here, in a way, we don't mind which one is true, and we don't mind if both of them happen to be true. So thinking about what's then going to happen with our inputs and outputs, we only get 0 here when both inputs are 0, and all other combinations are going to give us an output of 1. Now, a situation where an OR gate might arise is, let's suppose now I'm looking for a holiday. I'm searching for a holiday online, and perhaps I am interested in either a, let's say, a city break or a beach break. So in that situation, I haven't yet made a decision, so I would like to search and sort holidays. It could be city or it could be a beach break. And if the suggested destination happens to be both, let's say Rio de Janeiro in Brazil, then that's great. Then we don't mind both of them being true. Now, in terms of what happens passing through our logic gate, again, if we have both inputs are turned on, then the OR gate is going to output 1. That's fine. We just need at least one of them, remember. If we have one of them on, one of them off, then again, that's fine. We're going to get an output of 1 of true. Swapping the order doesn't matter. We only needed one of those things to be true. So again, we're going to get our output of 1. And it's just this final case when both of those things aren't true, when we're going to get our output of 0. And again, we can summarize all of these inputs, combinations of inputs, alongside the outputs from the OR gate in our truth table. And again, this is just summarizing what we've seen on those previous slides. The next gate is something called the XOR, as it's written, or we read this as exclusive OR. And the name is kind of telling you what this gate is doing. So it's very similar to the OR gate, the one that we've just been looking at, except now we do not want both things to be true. So in this sense, if exactly one input is 1, and it must just be one input going in as being true, that's when we get 1 as the output. We get a 0 in any other situation, which would mean if we put in 2 zeros or 2 1s, the inputs are the same, that's when we get our output of 0. Now, an example of an exclusive OR gate, thinking back to my online searches, perhaps this time I'm interested in hiring some kind of vehicle. I'm going on holiday and I need a mode of transport. Then I might say I would like to find all items that are cars or motorbikes, but I don't want both to come back. I don't want to hire both a car and a motorbike. I want to hire either a car or a motorbike rather than both. So that would be an example of an exclusive OR situation. Now, rather than showing you the machine this time, I think the best way to understand the exclusive OR is to actually look at our truth table for the OR gate, so going back to where we were before, and then just thinking about what does the exclusive OR do. So we know it's the same, except we rule out this first case. So for the exclusive OR, we just change that value for the two inputs both being on. That one just gets turned into a 0. So again, just to see that for the OR gate, those two being together give us the 1. And then for the exclusive OR, that gets changed to a 0. So again, it's very similar to the original OR gate. Now, next up, we can talk about negatives, negating gates. So the NOT gate does hopefully what you would expect. So whatever your input, the NOT gate says change it. So here, if we input a 1, the NOT gate changes it to a 0. It's not 1. And if you input 0, the NOT gate changes it to the 1. So the NOT gate just flips whatever the input was in that situation. Now, the NOT gate is very helpful because we can now combine the NOT gate with those other gates that we've talked about. So the NOT gate can be applied in combination with the AND gate, the OR gate, and the exclusive OR gate. And these all have fun names. So when we apply NOT alongside AND, we call it the NAND gate. So NOT AND. And what that's going to do is or the way I like to think about it at least, is I think about what the AND gate does, and then it just flips everything. And we'll see that in the truth table in a moment. The NOR gate, so not OR, again, is the combination of the NOT gate and the OR gate. And so what that does is it produces the opposite output of the OR gate. So again, we have our truth table for OR. We just flip those values. And then finally, we have the mathematician in me wants to say N XOR to follow this pattern, but it is more familiar to use the term XNOR. But what it means is we are applying the NOT gate to the exclusive OR. Again, it's kind of nicer to say XNOR as written here. But what that's doing is producing the opposite of the XOR gate. So just to see those in action in our truth tables now, this would be our AND gate. So again, A and B gives us just the 1 in the top row. And then for the NAND, we want the exact opposite. So that column is just going to completely flip at the end. So the 1 with the 3 zeros has become a 0 with those 3 ones. And the others are going to do the same. So again, if we think about A or B, this would be our output. And then A nor B, we're just going to flip. So the 1, 1, 1, 0 becomes 0, 0, 0, 1 in those rows. And then finally, for the exclusive OR gate, again, if we write out what will happen for exclusive OR, then when we do the NOT gate applied to that, we get 1, 0, 0, 1. Those values are flipped as well. And that's it. They are the 7 fundamental, they are the 7 foundational logic gates, which can be used to build much more complicated systems, which we'll see soon. Not all logic gates are created equal. Some are much more powerful than others and can be used to construct. No, let me say that again. Sorry, not all logic gates. Not all logic gates equal. Okay. Not all logic gates were created equal. Some of the Thomas. Right. Okay. Some logic gates. Some logic gates can be used to create all others. Some logic gates can be used to create some logic gates can be used to create all others. Okay. Not all logic gates were created equal. Some can be used to create the others, and these are known as universal logic gates. And that's a fire alarm. Not all logic gates were created equally. Some, known as universal logic gates, can be used to construct all other logic gates. Let's have a look at which ones they are. So the key to a universal logic gate is going to be NAND and NOR. So these gates alone, so just NAND by itself, or alternatively just NOR by itself, can be used to actually build all other logic gates, so AND, OR, NOT, etc. And it's for this reason that NAND and NOR are referred to as the universal logic gates. Now let's have a look at how we can combine them with themselves to get these other gates. So here we have an example diagram, and I'm purposefully not yet going to reveal what this gate is demonstrating. So we have two inputs, which is going to be a single input A but repeated. And this is going to be fed through our NAND gate. And of course, we must have these two inputs with it being a NAND gate. And then that is going to give us an output. And this represents one of our foundational gates. As we can see, it's built entirely from a NAND, but it is behaving in a different way. So let's try and unpack this and see what this is showing. So to begin, we can write out possible input values for our input A. So A, of course, is coming from our two-element, our Boolean set. So they are going to be 0 and 1. And again, we've got two columns here in our truth table to show that that input is being repeated. So if we have the input 1, then again, we copy that. So we now have two 1s entering our NAND gate. Now, the way I like to think about these negative gates is in my head, I think about, well, what does an AND gate do? So 1 and 1 is going to give me a 1 if it was an AND. However, it's a NAND, so it's going to flip that and give us a 0. Now, the other input that could happen is, of course, 0. So if A is equal to 0, again, we copy it. We are inputting two A's into our NAND gate. So both of them are off. We have two zeros. So again, the AND gate would remain off, which means the NAND gives you the opposite. So that's going to give us the 1, and that was going to be true. So what we can see here, if we now think about what gate have we displayed in this diagram, we've got a 1 going in and a 0 coming out, and we've got a 0 going in and a 1 going out. So hopefully you recognize that this is exactly the NOT gate, as shown over here. The first column of our truth table and the last one are exactly what we're seeing for the standard NOT gate truth table. Now let's look at one more. So now that we've built the NOT gate, let's see if we can use it to create something else. So if we think about a standard NAND gate, so now we're going to have two inputs, A and B, being fed through our NAND gate, which remember stands for not AND. And we've just seen how to use a NAND gate alone to construct a NOT gate. So if we have a NAND and then we apply a NOT, it's going to reverse the NAND. So once you reverse something that's already been reversed, you get back to where you started. So this should, I believe, feed us through here. A and B go through the NAND, which then goes into the second NAND. But here we know that this is our NOT gate from the previous slide to then give us an output. So altogether, this should give us an AND gate. But once again, let's check this by filling in our truth table. So as before, we will add column here A and B for our different inputs. I've also added here an intermediate column C, as shown in the diagram, to help us keep track of what's happened after that first gate. And then from C, we can then pass it through our NOT gate to get the output. So the possible pairs of values that we can enter would be 1, 1, 0, 1, 1, 0, 0, 0. Now, as we pass them through the NAND, let's just think about what happens. So 1 and 1. So again, an AND gate would give us a 1, which means the NAND flips it and is going to give us the 0. And then if it was an AND gate, everything else would be a 0, which means for the NAND, all of the others are going to be 1s. So for each of these pairs of inputs, we now know the intermediate step. And now, because we've already deduced exactly what this diagram represents, remember it's our NOT gate, then we can just flip these values to get our final output. So as C is doubled and passes through that final section, we know it's just going to give us the opposite. So the 0 becomes a 1, and all these 1s become 0. So now if we look at the first two columns, A and B, and we think about what we're seeing in that final column, we've got a 1 and a 1 outputting a 1, and all of the other combinations are outputting a 0. And we can see here, comparing this directly with the AND truth table, we can see it's exactly the same behavior in our more complex logic gate construction. But importantly, we've been able to construct the AND gate using only this universal NAND. Now you can continue in this way, drawing these diagrams and filling in these truth tables to construct all of the other gates. I've got a final example to show you, and this one is an OR gate, but I will leave you to fill in the truth table to see what happens. So we've been able there to use the universal NAND gate. We could have also used the NOR to construct the same other logic gates. I just chose NAND in this particular lecture. And what we've seen is how we can use NAND to get a NOT gate, to get an AND gate. I've shown you the diagram for an OR, and you can take this further and also use it to get the XOR, the NOR. Can I just do the ending again?
Yeah.
Sorry, I mumbled and got lost on the ending. I think I was all right until that point. I'll leave you to fill in the truth table for that one. So as we've seen, using universal logic gates to create the others can lead to some quite complex problems. And speaking of complex problems, I have one final mystery which I would like to try and solve. But for that, I'm going to need my thinking cap.
Awesome. How'd that feel to you?
That felt good to me. Yeah, that felt good to me.
It all comes through in the end, man.
Yeah. My brain's just buffering. That's what's happening.
And your voice is staying strong too, despite.
I can tell it's still croaky, but yeah, it's holding on. It's holding on. Okay. Welcome to my office. Shortly, I will recap to you the most difficult mystery that I've had to solve as a detective. But before that, I would just like to introduce this type of problem with some history. So the type of problem that I'm going to be solved is a logical puzzle referred to as an Einstein puzzle, as supposedly this type of problem was regularly, damn it. I did the click as good as really well. Okay, I guess. Welcome to my office. Shortly, I will recap for you the story of one of the most difficult mysteries that I've had to solve as the great mathematical detective. But before I get to that, I would just like to introduce the history of this type of problem, commonly referred to as an Einstein puzzle. Now, as the name suggests, this is a type of puzzle that was solved and preferred by Einstein when he was a child. And he particularly enjoyed solving these riddles or puzzles because, given a set of clues, he liked to then work through the logic of those clues to try and come to the only possible or the only plausible solution to the initial question that had been posed. Much like trying to solve a mystery or trying to solve the story of who owns the zebra, which is exactly the story that we will be investigating today. The story goes that a client approached me in my office and asked for some assistance with identifying the owner of the zebra of somebody who was living on their street. And they did helpfully provide me with an envelope filled with a series of clues to assist in my investigation. And they did also tell me some rules that would help when trying to solve the puzzle. Now, the rules that we need to help us to begin with this logical puzzle are as follows. So first of all, okay. Can I just carry on from there? Because I'm guessing we would show the slides here anyway.
Yes, if you just want to rewind to right before the slide, that'd be great.
The rules, yeah, okay. Okay, so I said the question we're trying to do is who owns the zebra? Okay, and then here's the rules. Okay, fine. My question I'm trying to solve. Sorry, I just need some water. To solve the question of who owns the zebra. Now, fortunately, my client has also provided me with a list of rules or a list of conditions that must be satisfied to help us to get to the bottom of this mystery. Now, the first of those rules is that there are 5 houses on their street, and all of these houses are in a row. So they are numbered 1, 2, 3, 4, 5, where there is no neighbor next to number 1, so it just begins at 1, and there is no neighbor after number 5. Now, of those residents, we've been informed that each house is painted a different color. So there will be 5 different colors of those houses which we need to identify. We've also been told that the person living in each house is a different nationality. So again, we will need to work with that information and identify how these clues relate to this information. Our 4th rule, or our 4th condition, is that the person in each house also has a beverage or a drink that they are commonly seen enjoying. And there is a list of possible drinks, which includes tea, coffee, water, orange juice, and milk. And finally, we also know that I've not mentioned pets. Oh, God.
Is there a typo in the slide too?
One.
Okay. Different nationality. Okay. Each owner in the house also has a specific pet. They have a specific job, and they also have a specific drink that they enjoy, the list of which are shown on the screen. Now, importantly, of all of the occupants in those houses, they all have a unique and individual drink, pet, and job, so there will be no repeated entries when we are putting together all of our information. Okay, so now given the rules and the setup of the problem, our task is provided with this envelope of clues, information that our client has already sourced, but to this point has been unable to solve the mystery. They have collected all of this information, but they themselves are not able to use it to logically deduce who indeed is the owner of that zebra. And they are particularly annoyed about the person who owns the zebra, as all of that braying has been keeping them up at night, which is why they have enlisted the services of the great mathematical detective. Now, in this envelope, we have a series of clues that are going to help us to solve this problem. And now these clues, I will show for you on screen as well. So these clues, God damn it. Now these clues. Now these clues I will also show for you on the screen as well, so you can see the information that we are working with. There are 14 in total, and each of these statements is a true statement. So our task is, given all of this information, these 14 clues, and given the information about the occupants of these houses, which we can helpfully display in this table. Can we complete the table? Can we use the clues and the information to discover which person lives in which house and ultimately get to the conclusion of who owns the zebra? Now, as I mentioned, I have already solved this, being the greatest mathematical detective, and I would love to share with you all the process by which I was able to draw this conclusion using the tools of logic. So we begin by looking at our list of clues and thinking about which ones mention a specific house. So if we look at our list, we can see that number 8 and number 9 both mention a specific, So if we look at our list, we can see that clues, so if we look, okay. So if we look at our list of clues, we can see that both clues 8 and clues 9 mention a specific house, and so therefore we can immediately write that information into our table. So clue 8 tells us that milk is drunk in house 3, so we can fill in that value, and also we are told from clue 9 that the Norwegian person lives in house number 1. So we'll start simple and we will add those two entries into our table to keep track of the deductions that we have made so far. Now, where to go next is a tricky question. However, as the master detective, I was able to realize that since we have now placed the Norwegian nationality on the table, we actually have a clue that refers back to this. So if we look again at our list of clues, we can see that clue number, I've lost myself, okay. So we look back. So if we look back at our list of clues, we can see that clue number 14 mentions that the Norwegian person is next to the blue house. And since we have already placed Norway on our table, we can now add, next to this, we can add blue to house number 2. Now, from here, we might go back to our list of clues. And we might want to think about, well, given we have placed blue, what other house colours might we be able to figure out? So if we highlight the clues that mention a house colour, so here we can see that is clue number 1, clue number 3, 5, and 7. Now there's quite a lot going on here, but if we just spend a moment and think about when those colours are mentioned and the fact that a lot of them are actually coming in pairs. So what I mean by this is the first clue tells us that the red house must go with the nationality of being English. So if we now look at our table and we focus on house 1, we can deduce that house 1 cannot be red because red has to go with England, the nationality, but we already have filled in Norway for house 1. So therefore, house 1 cannot possibly be red. We do not know where to place red, but we know for sure that house 1 is not red. Now, if we look again at our list, we can see that coffee is mentioned alongside the greenhouse. At the moment, we can only deduce that house 3 cannot be green because house 3's beverage is milk, but that doesn't help us necessarily with house 1. Going back to our clues, we then have the greenhouse being immediately to the right of the ivory house. Now this is a very interesting clue because this tells us that green and ivory are actually coming together as a pair in our table. So we need 2 successive empty spaces in the color row. So with that in mind, we can say that green could possibly go in house 4, provided ivory was in house 3. They have to go in next to each other. Green must be to the right of ivory. Or we could put ivory in house 4 and then green would go in house 5. You'll notice, however, that both green and ivory cannot go in house 1 because they must come as a pair and house 1 has no space to have something next to it, which now actually allows us to get to a conclusion. So remember we said that red cannot be house 1 because the nationality is already filled. We already have Norway and red must go with England. We know that green and ivory go as a pair, so they cannot also be house 1. Which means the only remaining color is yellow. So we can now actually conclude, again, using our tools of logic, our logical deduction, that house 1 must in fact be yellow. And from our clue, we were told that yellow is related to the teacher. So our clue 7 allowed us to put yellow and teacher in there together. Okay, so now we've made some progress. Let's go back to our list of clues and look at which ones we have remaining. I've just lost my train of thought for a second. What am I doing now? Okay. Right. Welcome to my office. We are going to be solving a type of problem called an Einstein puzzle. These are logic problems which were supposedly very popular with the man himself when he was a child. The idea of an Einstein puzzle is, given a series of statements, we then have to answer a seemingly simple sounding question. However, to get to the answer of that question, we must use all of the statements or the clues and our powers of logical deduction. Now, the question we are going to try and solve today is, who owns the zebra? And the rules of the problem are as follows. We have a series of characters. These characters or occupants are going to live in houses numbered 1 through to 5. And again, our task is to identify which one of them owns the zebra. Now, those houses are going to be in a line, and they're going to have so number 1 has no neighbor apart from 2, and number 5 only has a single neighbor, which will be number 4. We also know of these occupants that their houses are all painted a different color, so we will need to work out which color corresponds to which house. We also are told that in each person, sorry, not each person, we also a different color. We are also told that in each house, the person has a different nationality, as well as having a different favorite drink, a different job, and they keep a different pet. Again, we're trying to work out which one of them has that zebra. The possible drinks are listed on the screen. And finally, just to make sure we've crossed all those T's and dotted all those I's, we also know that no one has the same job, pet, or taste in beverage. So there will be a single entry for each one of those categories, each one of those items. Now, the way we are going to do this is to work our way through the series of clues and try and figure out what we can deduce about the location of that particular person or that particular item. Now, the series of clues is quite long. We have 14 clues in total, which I have here in my envelope. And we will look through these in groups, not necessarily in the order they are written, but depending on which ones we feel could be the most useful to help us make progress in our investigation. And what we're going to do to keep track of our investigation as we work through these clues is we are going to fill in the values in this table. So down the side, we have our 5 categories. We have the nationality, the color of the house, the pet, the job, and the drink. And across the top, we have the houses as they are numbered. So that's the setup. Being the great mathematical detective himself, I have already, of course, worked out the answer. However, there are many, many steps involved. And so my plan here is to talk you through those many steps, and I really do encourage you to follow along and try to solve this mystery for yourselves. So we will begin by looking at our list of clues, and in particular, we will look at clues 8 and 9, which explicitly mention numbered houses. So here we can see that clue 8 tells us that milk is drunk in house 3, so we can immediately place that on our table. And we can also see that the Norwegian person is the correct nationality for house 1. So again, because they mention explicit house numbers, we can just write those values into our table. Now that we have some entries, we can go back and look at our list of clues, and we can cross off those 2 clues that we have used. And we will do this just to keep track of the information that we have already used to draw conclusions from. Now, since we have now placed Norway, it's very helpful if we now look at clue 14, because this mentions the nationality of Norway. And it tells us that the Norwegian person is going to live next to the blue house. So given we have already placed Norway, if we go back to our table, we now know that blue must be the color of house number 2, because it has to be next to the Norwegian, and the Norwegian is in house 1, so their only neighbor is house 2. So this is how all of the clues can be used to help us to build up all of the entries in this table. So again, we'll go back to our list. We've now crossed off 3 of our clues. We're making good progress, but still another 11 to go. So perhaps next we might look at a series of clues that mention a particular color. So here we've got clue 1, which pairs together England with red. We've got clue number 3, which pairs together coffee and green. We've got clue number 5, which rather than being a specific pair of categories or a pair of information, is actually telling us something about the relative colors, the position of those colors. So it's telling us that green and ivory actually go side by side in our table. And specifically, green goes to the right of the ivory entry. And as we're going to see in a moment, that's going to be a really helpful piece of information. And then in clue 7, we again have another pair that yellow and teacher must go together. So now if we keep these in mind, all of these different pairings, and we go back to our table, then if we focus on house 1 in particular, and we think about which colors could go in house 1. So first of all, we saw that red had to go with England. So red and England cannot go in that first column because we already have the nationality as Norway. So that allows us to conclude, we can deduce that house 1 cannot be red. So therefore red must go somewhere else. Now, what other color could house 1 be? Well, the remaining options are green. We could also have ivory, and we've also got yellow. Now, green and ivory, if we go back to our clues, came together as a pair. So we've said that wherever you write ivory, green must immediately go to the right. So if we think about the location of house 1, if we were to write either green or ivory in the color row for house 1, then that's going to actually be a contradiction. We cannot fit both of them in. So house 1 cannot be red, and also because they come as a pair, it cannot be green or ivory. So we're actually now in a position where we've drawn a conclusion. So we've kind of logicked our way through all of the possibilities, and we see that all that remains now is that this house has to be the last remaining color, which is yellow. So we can actually now add yellow to house number 1, and also from our clue, if we look again at number 7, we see that yellow goes with teacher. So we can add those two now to our table, and again, we're beginning to fill in more and more of those boxes. And I'm just going to pause for a second to see where I'm up to. Right. Having now placed teacher in that first column for house 1, if we go back to our list of clues, we notice that the 11th clue actually references the teacher. And it tells us the teacher is next to the house which has a horse. So here we're getting our first appearance of a pet, which is good because remember, it's going to be a long way, but we are trying to get to the answer of where the zebra fits in this table. So now we can add the horse next to the teacher. And once again, because the teacher is in house 1, the only available place that is next to that is house number 2. Having now placed the horse, again, we can cross off that clue. And now next, I decided to focus here on the drinks. So we've got a few different drinks that are mentioned. We can see there that coffee is going with the greenhouse. We've already looked at that clue before, but last time we were focusing on color. Now we want to look at the drink here and the use of coffee. We also can see that the Ukrainian nationality is going with tea. And also we got the doctor going with orange juice. Now if we look at our table and how all of these might fit. So remember, we've got coffee with green, Ukrainian with tea, and doctor with orange juice. So now if we look at what could happen with house 1. So again, we'll do these one by one. If we look at the first one, coffee must go with green. So house number 1, we already have a fixed color. So that tells us the drink cannot be coffee because we already have yellow in that spot. So it rules out coffee. Then if we look at tea, well, tea has to go with Ukraine. But again, if we look at house 1, we've already fixed the nationality with Norway. So we cannot put tea as our drink, which just leaves us with orange juice or water. Now orange juice has to go with the doctor. And again, we know that house number 1 actually belongs to the teacher. So once again, we cannot fit that as a pair. So we've actually, again, been able to rule out all of those possible drinks. So it cannot be tea, it cannot be coffee, and it cannot be orange juice, which again, through the process of logical deduction, tells us that it must be the last remaining drink, which is water. Okay, now again, going back to our clues, we actually haven't crossed anything off here because water isn't mentioned explicitly, but as we've seen, we are making progress with our table. Now next, we could go back and look at some of the colors once again. And this is actually one of the trickier parts of our pathway through the solution to this problem. Because at this stage, we realize that you actually cannot immediately fill in any of those remaining colors. So we've got England going with red, we've got coffee going with green, and we've got this pairing of green and ivory. And if we think about where all of these could fit, actually most of them in fact can fit across 3, 4, and 5. We do not have enough information about 3, 4, and 5 to rule out where those remaining colors could go. What we do know, however, is that green and ivory have to go as a pair. We have to go green to the right of ivory. So one option, and because it's an option here, I'm just going to highlight this in a different color. One option here is to put ivory and green in 4 and 5. That works, they are next to one another, and that would mean house 3 would be red, and again, we have no contradiction at this point. But we could also put ivory and green in house 3 and house 4, and then red would go in house 5. And again, this doesn't at this stage lead to a contradiction. However, the way to make progress is to pick one of these pathways, and we can picture this as a pathway opening out in front of us. It's a little like playing a Sudoku puzzle and you reach a difficult part and you have to guess if it's a 1 or a 2 and see which one works and which one doesn't. We're at that fork in the road. Now, as I have already solved this problem, I can help us out and say that the one that we want is actually the original placement. So if we had ivory in 3 and green in 4, then that would actually lead to a contradiction. It would be impossible to satisfy all the remaining clues with those boxes in the table. So that then tells us, because that one doesn't work, tells us it must in fact be the current setup where we put ivory in 4 and green in house 5. Now that we know this, we can then add in the other information. So we know that green goes with coffee. That was one of our clues, so we can put coffee in. And we've also now got the final spot, which was red, and red went with the nationality of English. So suddenly, again, we're now really getting quite far along with the table. It's starting to look quite full. And crossing out all of those clues that we've just used, we can see that we don't have that many more to work our way through. And I'm just going to pause because I've lost where I'm going. At this stage, we're in a very similar situation to a few steps back, in the sense that looking at our list of clues, it's actually, once again, not immediately obvious what we should do next, or how we might be able to fill some of those remaining spaces. Now, what I decided to do when I was solving this was to actually look again at the beverages. So here we can see that we've got the Ukraine nationality going with tea and the doctor job going with orange juice. However, if we look at our table, we can see that both of those pairings could actually fit in either house 2 or house 4. So there's nothing ruling out the tea going in house 2 or house 4 and the orange juice going in house 2 or house 4. And this is once again a fork in our road. This is again a fork in our pathway through to the solution. So at this stage, if we were to try, for example, the doctor and the orange juice, which again come together as a pair according to our clue, if we put those for house 4 and we were to continue this forwards, it turns out that that is actually going to lead to a contradiction and going to cause, oh no, that's wrong. It's the other way around. Okay. Should I re-go from where we broke, or? Yeah, okay. So I just done that. Sorry, I just got them muddled up the wrong way around in my head. Okay. Okay, so I'm just going to say, okay, right, okay. So, okay, cool, yeah, let's try again. Sorry.
Yeah, you can go ahead and begin whenever you're ready.
Okay. So now at this stage, okay. At this stage, we are once again at a fork in the road in our solution, in the sense that, looking at the list of clues that are remaining, there are no clues that we can just immediately place into our table. So what we've decided to do here, what I've decided to do here, is to look at the drinks. So we have 2 remaining spots to place drinks. We've got orange juice, which must go with doctor. That's a pair from clue number 12. And from clue number 4, we've got Ukraine alongside tea. Now, if you look at our table, we could position the doctor and orange juice in house number 4, for example, like shown, or we could position it in house number 2. And in both cases, we could still position Ukraine and tea. So neither would lead to a contradiction immediately. However, just as before when we had a fork in the road with green and ivory, if you follow through the current placement, so if you put doctor and orange juice in house 2, and you follow that through to its logical conclusion, we again see that there is a contradiction. It's not possible to complete the table and satisfy all of the clues. So again, that, like before, that tells us that the correct way forwards here is going to be doctor and orange juice going in house number 4. Now we are very close to solving this problem. So having this problem. So now we are very close to having solved the problem. So having fixed doctor and orange juice there in house 4, we can now add Ukraine and tea, the other pairing that we were thinking about, to complete the row of beverages to go alongside our completed row of house colors. And again, we are very nearly there. So let's look at which clues are remaining. So on our list, a lot of these have been crossed off. And the one that really jumps out to me now is actually down the bottom in clue number 13, where we have the baker paired up with Japan. Because if we now look at our table, so we have a job and a nationality together. And looking at our table, if we were to try and place this in house 2, for example, that wouldn't work because we have a nationality already there. If we were to try and place this in house 3, similarly, it wouldn't work. It wouldn't work for house 4. So the only available space for both a job and a nationality is house 5. So again, through our logical deduction, we have to place that clue. Japan and baker must go for house number 5. So again, we can cross off that clue. And at this point, I think we could probably just work our way through the remaining clues from the top through to the bottom. So the next one tells us that the nationality of Spain must go with the pet being a dog. if we go to our partially completed table, we see that where is there a gap for nationality and pet at the same time? That is only in house number 4, so we can fill in Spain and dog over there. The next clue along is telling us that the carpenter owns snails. So there we've got a pet alongside a job. So going back to our table, where is the remaining space for pet and job? That's going to be house number 3. So we can write in there snails and carpenter. And then almost finally, we've then got clue 10, the gardener living in the house next to the man with the fox. So this tells us we need a job space that's next to a space for a pet. So again, if we go back to our table, that's going to be houses 1 and 2. So we can fill in those final values, which then leaves us in the situation of the only remaining pet, which is the zebra or the zebra, which is going to have to go in house number 5, which means the answer to the original question posed at the beginning, who owns the zebra, is going to be the occupant of house 5. And I'm going to pause because we have to do an ending. As we've seen, these Einstein puzzles, whilst being very fun, can be quite involved and require a lot of steps, a lot of patience, and a lot of practice. They are, however, an excellent demonstration of the power of logical deduction. Now, on to the next case. In this chapter, we have used the principles of logic to solve a range of problems. We began by looking at how to follow an assumption through to its logical conclusion with the werewolf puzzle. We then defined a logic gate and looked at how we can use logic gates to build more complex logic systems, including the universal logic gates NAND and NOR, and how they themselves can be used to construct all other logic gates. We then ended by solving a final, difficult mystery puzzle in the form of an Einstein puzzle, which required the most almost, which required In this chapter, we have used the principles of logic to solve a wide range of problems. We began with the werewolf puzzle, where we followed through our assumptions to their logical conclusions. We then moved on to logic gates, which are the building blocks of more complex logic circuits. We looked at the AND gate, the OR gate, the NOT gate, and then we combined them in a special way to create the universal logic gates, NAND and NOR, which can be used to build all other logic gates. We then finished with a final problem in the form of an Einstein puzzle to demonstrate our mastery of logical deduction, which means the logical next step is, of course, to look at functions, which is where we'll be going in the next chapter.